Okay, this is Applications of Aqueous Equilibria. This is the last part of Chapter 15. It's going to cover sections 15.4 through 15.7. In this lesson, we're going to talk about titrations and pH curves, acid-base indicators, solubility, and Ksp and qualitative analysis. So we've got quite a bit to cover, but it's not really too much difficult stuff. Pretty much common sense. We're through the rough stuff. So let's take a look at some pH curves. In this first titration, we have titrated 50 mils of a 0.2 molar HNO3 solution with 0.1 molar NaOH. So we have a strong acid and a strong base. So you can figure out what's going to happen here if you just use like MAVA equals MbVb. You can see that if you've got 0.2 times 50 equals 0.1 times X, that your X is going to be 100 milliliters. So it's going to take 100 milliliters of the base in order for the solution to be titrated. And remember, when we talk about equivalence point, we're talking about when the moles of H equal the moles of OH, so that would be at a pH of 7. And here you have a strong base titrated with a strong acid. You can always tell what's being titrated with what by looking at the curve. If the curve starts at the bottom here, that means that you are starting with an acid and titrating with a base. If the curve starts at the top, you know that you're starting with a base and you are titrating with an acid. And in this one, you had 100 mils of 0.5 molar NaOH. You titrated with 1 molar HCl. So if I have 0.5 molar times 100 equals 1x. Therefore, my HCl was equal to 50 milliliters. And that was my equivalence point. A couple of things: when you have a strong acid or strong base titration, your pH changes very little until close to the equivalent point. So you have lots of H and then added OH, it doesn't change the pH much. Near the equivalence point, there is less H, so added after the equivalence point, you add OH and whoosh, the pH shoots up. And then on the downside of the equivalence point, that's where we were talking earlier. Near the equivalence point, there is less H+, so when you add OH, it shoots up again. Okay. Let's talk about weak acid with a strong base. The amount of acid determines the equivalence point. The pH value at the equivalence point depends on the acid strength. The weaker the acid, the higher the pH at the equivalence point. And that should make sense, because if you have a weak acid and a strong base, you know that it's going to wind up basic. So in this one here on the left, we had 50 mils of 0.1 molar acetic acid, and we added 0.1 molar NaOH. So I'm not going to do the math on this, but the MAVA equals MbVb means that we had 50 mils of NaOH added. So I started with a weak acid and I added 50 mils of NaOH. And notice that the equivalence point is higher than 7. Now, why does that happen? If we have HC2H3O2, you know that that's a weak acid, so you're going to have barely any dissociation. But what's happening is that the acetate ion in solution is going to react with water and is going to form HC2H3O2 plus OH minus. So you've got these extra OH minus ions in solutions that's raising the pH so it's greater than 7. In this graph on the right, we're just comparing a strong acid versus a weak acid and a strong base. For a weak acid, strong base titration, the pH rises more rapidly in the beginning of the titration, then levels off at the halfway point due to buffering effects. And the pH at the equivalence point is higher than for a strong acid-base titration, which you can very easily see here. Here's the equivalence point of the strong acid, and the equivalence point of the weak acid is there. In these next two graphs, this is just showing you the relationship between Ka and titration curves. So this, my drawing is not as good as the one in the book, but you can look at it. In this, we had 50 milliliter samples of 0.1 HA, so some acid with 0.1 molar NaOH. And these are the various curves that they produced based on the different acids that were used in the trials. So what you can see from this is the weaker the acid, the greater the pH value at the equivalence point. The vertical region surrounding the equivalence point also becomes shorter, but this is the more important aspect of it. In the next diagram on the right, we have a weak base. You know it's weak because the pH is not starting up here where it's 14. Okay, it's starting down here somewhere, maybe about 8. And it's being titrated with a strong acid. How do you know this? Because if you have a weak base and a strong acid, you know that your pH is going to be less than 7, and that's what you see here. In this one, we had 100 mils of 0.5 molar HNO3, so you have a strong acid. Oops, sorry. NH3 with 0.1 molar HCl. And that's it. Okay, moving on. One special point when the pH equals the pKa, we have to understand what's going on. The pKa is the pH value at the half equivalence point. That is the point at which only half of the volume of the base needs to reach the equivalence point has been added. So half equivalence point is when the pH equals the pKa. So that would be this point right here where if you were to read this on the graph, it would be 4.75. So say that it took, we're going to make this easy, let's say that it took, I know there's numbers here, but let's say that it took 100 mils for this to reach the equivalence point. So that's all of it. Here, halfway, say this is 50 mils, okay? That's half of what it took to meet the equivalence point. That's where your pH equals your pKa. And I just use 50 and 100 because it's easier than reading the numbers on this graph. So that could come handy depending on what the problem is, what you're given, knowing that. Equivalence point is determined colorimetrically, which means using an acid-base indicator. To mark the end point. And we need to define end point, which is basically when the indicator changes color. And there's something important about that, and that is it may not be the same as the equivalence point. Okay. We can also use a pH meter. Plot the curve and find the center of the vertical region. How do you pick an indicator for colorimetric analysis? Do I just go in and grab the first thing I see on the shelf, or are certain indicators better to use than others? Well, actually you need to determine the pH at the equivalence point, either from a calculation or using a pH meter. And then you can choose the appropriate indicator from the chart below. So I know yours doesn't appear in color, but if you had the color chart, this would be what it looks like. So depending on where the pH is going to lie at the equivalence point, that would determine what indicator you would use. So let's look at a couple of examples. Here, the equivalence point is right here. So in this case, would you use phenolphthalein or methyl orange? Well, obviously you would use phenolphthalein, because this is about a pH a little higher than 9. So if you go back to your chart, pH around 9, you could use thymol blue. That wasn't a choice here. And here's the phenolphthalein, 8.3 to 10. I wouldn't suggest using the thymolphthalein because that's a little bit too close. But either the thymol blue or the phenolphthalein would be good for that. In this second one, your equivalence point is down here. So it's between 4 and 5. So let's look at methyl orange. Methyl orange is between 3.1 and 4.4, but it could be on the upper end there, upper end of the scale, so you could use methyl orange. It's certainly a better choice than phenolphthalein. And in this one, Notice this curve looks a little weird. This is a diprotic acid. So when you have a diprotic acid, you're going to have two equivalence points. Here's the first one, really hard to see. Okay, you have a little bit of a slant line, and that's halfway, and then here's the second one right here. So you have a diprotic acid. So you may have to use two indicators in this type of a problem. Polyprotic acid, you would see 3 equivalence points. How do indicators work? Well, we know they change color, but they're weak acids or bases. Weak acids. Most of them are weak acids or bases. And their partners have color and change when the equilibrium is shifted. So in this case, HIN yields H plus and IN minus. So if I were to add OH minus to this, what would happen is the OH minus would grab the H plus and make water. That would be decreasing the concentration of H plus, shifting right, favoring the forward reaction, and turn green. If I add H plus, it's going to cause a shift to the left and will turn blue. And we can see this same situation with phenolphthalein. We know that phenolphthalein is colorless to pink. So when I add base, it grabs the H, makes water, shifting right, and turns pink. When I add acid, it increases the H plus, shifts left, and eventually will turn colorless again. Each indicator has a Ka, and the color change occurs at approximately the negative log of the Ka. So for example, the equivalence point of a titration is 4.3. So you've got a pH equal to 4.3. And they want to know what indicator would be a good choice. And all you're given is the Ka values. So if you take the negative log of the Ka for all these values, you're going to get 1.6, 4.3, 5.2, 7, 10.6, and 10.4. So I think it's pretty plain to see the areochrome black T is the indicator that you would want to use. Okay, last section, solubility, equilibria, and Ksp. So just on a side note, we've studied Kp and Kc, and we just finished studying Ka, Kb, and Kw. And now I'm going to introduce Ksp. It is the last of the Ks, and it is the study of the solubilities of insoluble ionic compounds. So when we say something, when we think about NaCl no-so, and we say something is insoluble, meaning it forms a precipitate, everything is slightly soluble, but it is so minuscule that we say that it is not soluble or it forms a precipitate. Well, in this section, you're actually going to calculate how soluble that insoluble compound is. All right. So this is going to be pretty easy because it's a review of a couple of different things that we've done before. So the first thing, in order to write a solubility product expression, if you remember, anytime we write any type of expression, we have to have a reaction. So CaF2 is a solid, and it's going to dissociate into Ca2 plus and 2F minus. And from that, we can write our Ksp expression, Ksp, products over reactants. So this is going to be the concentration of Ca2 plus times the concentration of F minus squared. And that's it. Because if you remember, solids are not part of a K expression. Let's do another one. So in this one, you've got a solid, and you're going to have 3Mg 2 plus 2PO4 3 minus. Therefore, your Ksp is going to be equal to Mg2 plus cubed times the PO4 3 minus squared. And BaSO4, it's going to be Ba2 plus SO4 2 minus. Ksp equals the concentration of Ba times the concentration of SO4. Ksps are very, very tiny, and you can find them on A24 in the appendix of your textbook. So let's get into problem solving. The solubility of a copper 1 bromide is 2.0 times 10 to the negative fourth molar. What is the value of Ksp? So the first thing we want to do is write a formula. So Cu, they're saying it's plus 1, Br is minus 1, so it's simply CuBr. Solid, Cu plus 1, almost wrote plus 2, so used to writing that, minus 1. So our Ksp is going to be equal to the concentration of Cu plus 1 times Br minus. Oh, just a note, you were given in your note packet a page with Ksp values on them. Please don't use them because Ksp values change depending on temperature. And I don't know what temperature these are at, but they're certainly not room temperature because I looked in the appendix on A24 and some of the Ksps don't match what's in the back of the book. So please just either rip this out or put an X through it. We don't want to use these. We want to use ones that are at standard temperature, which are in the appendix on A24. So what do we know? We know that the molarity is 2 times 10 to the minus 4, and it's the ions are 1 to 1, so that's the molarity, the ions. So if we were solving this, we could say Ksp equals x squared, and we know that that's going to equal 2 times 10 to the minus 4 squared. So my Ksp equals 4 times 10 to the minus 8, and that's my Ksp. And if you recall, that has no units. What is the molar solubility of silver sulfide? So silver sulfide is Ag2S. So I write my reaction. This is solid. So I've got 2 Ag plus S2 minus. Okay. So there's a couple of things going on here. First, if I write my Ksp expression, that's going to be equal to Ag plus so I have to think about this from a variable point of view. So if I have 2Ag, that's kind of like saying 2x. Sometimes people use S here. I think the textbook uses S for like solubility. It's up to you. I rather just use X, but you can use S. And this is going to be X. We can look up the Ksp of silver sulfide, and we see that it's 1.6 times 10 to the negative 49. And that's going to equal the concentration of, so we've got 2x, and it's squared, times x for S minus. So 2 times 2 is 4, so this is going to be 4x squared times x, which is going to give me 4x cubed. So 1.6 times 10 to the negative 49. So I divide both sides by 4, take the cube root, and x equals 3.42 times 10 to the minus 17 molar. So what that means is if I had a beaker, that I'd have a whole bunch of precipitate on the bottom, but in solution I'd have Ag plus, a little bit of Ag plus, S2 minus, S2 minus. The concentration of this solution above the precipitate is 3.42 times 10 to the minus 17 molar. So extremely, extremely small. Okay, let's look at another problem. What is the molar solubility of bismuth 3-sulfide? So we've got Bi, this is plus 3, S minus 2, so Bi 2S3 solid into 2 Bi 3 plus 3 S2 minus. And these are aqueous over here because they're in the water. Should have wrote that. So we need the Ksp of bismuth 3 sulfide, and that's going to be equal to 1.6 times 10 to the negative 72nd. So what do I have here? Well, I should just write the Ksp expression with the concentration. So this is going to be Bi 3 plus squared times S2 minus to the third. So remember, this is the same as 2x. This is the same as 3x. So this is going to be 2x squared, 3x cubed. So I've got 2 times 2 is 4, so I've got 4x squared times 3 times 3 is 9, times 3 is 27x cubed. So this is going to give me 27 times 4, 108 x to the fifth. 1.6 times 10 to the negative 72nd. So I divide both sides by 108, and then I raise it to the 1/5 power, because I don't think we can do that on our calculator. If I take 1.6 times 10 to the negative 72nd divided by 108, you should get 1.48 times 10 to the negative 74 raised to the 1/5 fifth power. And that's going to give me an X equal to 1.7 times 10 to the negative 15 molar. So that's my answer. What is the molar solubility of iron 3 hydroxide? It says silly hydroxides. I'd prefer to call them pain in the butt hydroxides, and you'll see why in a moment. So FeOH3 solid dissociates into Fe3 plus 3OH minus, and these are aqueous. Okay. So something special about hydroxides is that not only do you have Fe3 plus in here and OH minus, but you also have water which autoionizes, producing H plus and more OH minus. And this only happens with hydroxides. So our Ksp is going to be equal to Fe3 plus OH minus to the third. So here's my X, but my hydroxide is going to be 3X plus 1.7 times 10 to the negative 7. And that's going to be cubed. And this is here because of the fact of it's a hydroxide and water is autoionizing. So what does that do to all my math here? Well, Ksp of iron 3 hydroxide, when we look it up on 824, is 4 times 10 to the negative 38. And that's going to be equal to this whole lot, X plus 3X plus 1.7 times 10 to the negative 7 cubed. And this I can put in my solver. So in my solver, what I'm going to put is, oops, this should be times. I made a mistake. Yeah, this is going to be X times 3X. My bad. Okay. So in my solver, I'm going to put X times 3X plus 1.7 times 10 to the minus 7 cubed minus 4 times 10 to the negative 38. And then I'm going to hit equal, and I'm going to put in a really, really small number because you see what we're dealing with. Our exponents are negligible. So for our X value, instead of taking 10%, your guess is going to be like 0.00001 alpha solve. And you wind up getting X equal to 4.0 times 10 to the negative 17 molar. And that's your answer. Now, just like an extension on this type of problem, I haven't seen it in a while, but they could say, what is the molar solubility when the pH is 5? So if you know the pH is 5, then you know your pOH is equal to 9, and therefore you know that the OH minus concentration is equal to 1 times 10 to the minus 9. So in that case, what you would do is, going back to your original equation right here, you would do Ksp equals 4 times, can't write, Ksp equals 4 times 10 to the negative 38, which equals x times, and you would put in your value 1 times 10 to the negative 9 cubed. And when you solve for that, you're going to get x equal to 4 times 10 to the minus 11 molar. So that's just an extension of how this problem could be changed. All right, we're almost done. Will a precipitate form? How do you know if a precipitate form? Well, just like we used to compare Q to K, we're now going to compare Ksp to Qsp. And Qsp comes from the initial value prior to an equilibrium shift. So if the Qsp is greater than the Ksp, then a precipitate forms. If the Qsp is less than the Ksp, then no precipitate. So, will a precipitate form when 50 mils of 0.00025 molar sodium phosphate is mixed with 50 mils of 0.0025 barium chloride? Will a precipitate form? Show all calculations and support your answer. So what you have to realize is that basically you have a beaker and you've got Na plus ions in here, and you've got PO4 3 minus in here. And in your other beaker you've got barium chloride, and you're going to mix them. Well, there's a couple of things that you know right away that you're not going to be interested in. You're not going to be interested in Na because Na combines with everything. And you're not going to be interested in the Cl because Cls are always aqueous unless combined with silver, lead, or mercury. But go ahead and write the reaction. You've got Na3PO4 combining with BaCl2, and that's going to form Ba3PO4 2, which is a solid, and NaCl, which is, is aqueous. So obviously I was correct in my assumption that the spectators were the Na plus and the Cl minus ions. So Ba3PO4 2 solid dissociates into 3Ba2 plus aqueous and PO4 3 minus aqueous. I'm missing something. 2 plus 2 PO4 3 minus. So my Ksp is going to equal Ba2 plus cubed times PO4 3 minus squared. The Ksp for this is going to, well, actually, we need to know for precipitates form. So we're not actually solving for Ksp right now. We're solving for Qsp, and that's going to equal let me backtrack. The Ksp of the barium phosphate, if we look up on page A24, is 6.0 times 10 to the negative 39. So we have to calculate the Qsp so that we can compare it to the Ksp. Now remember, up here, I'm going to go back and put it underneath so you see it. So since we already have values, we've got 50 mils of 0.0025 molar Na3PO4. So that's going to give me 1.25 times 10 to the negative 4. 1.25 times 10 to the negative 4. And that's going to be squared because of this. And then I've got 50 times 0.0025 of the BaCl2, which is going to give me 1.25 times 10 to the minus 3, and that's going to be cubed. So when I solve for my Qsp, I get a value of 3.05 times 10 to the negative 18. So let's compare this value to this value. Well, my Qsp is definitely greater than my Ksp. So Qsp is greater than Ksp, therefore precipitate forms. Okay. Sodium chloride is added to 50 ml beaker that contains a mixture of, this should say of, 0.00015 lead 2 nitrate and 0.00035 silver nitrate. Now they want to know which precipitate will form first. So in this beaker I have Pb ions, and I've got silver nitrate. And I'm going to add sodium chloride to it. So now I've got Na plus and Cl minus. So what do I know? What's going to happen? Well, we know all nitrates are soluble, so they're out. And we know that Na is soluble, so that's out. So I've got PbCl2 forming, and I've also got AgCl forming, which are both precipitates. So they want to know which one of these is going to form first. So we have to solve them as separate problems. So I've got Pb2 plus 2Cl minus, and these are aqueous. And then over here, of course, I've got Ag plus Cl minus. Remember, this is like saying x and 2x. So I've got a Ksp equal to Pb2 plus Cl minus squared. My Ksp of lead chloride from A24 is 1.6 times 10 to the minus 5. Now, what do I know that I have here? I've got 0.00015 lead, so I know my lead, so that equals 0.00015 times, and this was 2x squared. So I knew what this was, so I didn't have to use this x. I could just put the concentration in. So now, when I solve for x here, I'm going to get 0.163 molar. Now I'm going to do the same thing over here. This is x and x, and I've got a Ksp equal to the concentration of Ag plus times Cl minus. My Ksp for silver chloride from A24 is 1.6 times 10 to the minus 10. However, I know my silver ion concentration is 0.00035 times x. And when I solve for x, or s if you're using s, you get 4.57 times 10 to the negative 7 molar. So the one that will form first is silver chloride. So you've got Ag plus in here, and you've got Cl minus, and you've got Pb2 plus in here. When the concentration of this solution is equal to 4.57 times 10 to the minus 7 molar, which is strong, the AgCl will start to form. The PbCl2 will not start to form until the concentration of the solution in the beaker is 0.163 molar. Last page. Competing precipitate. How much remains? At 25 degrees, the solubility product constant Ksp for strontium sulfate is 7.6 times 10 to the negative 7. The solubility product constant for strontium fluoride is 7.9 times 10 to the minus 10. So what is the molar solubility of SrSO4 in pure water? So this is a straightforward problem. They want you just to solve for the molar solubility. So we've got Sr2 plus SO4 2 minus. Our Ksp is equal to 7.6 times 10 to the minus 7. And this is basically x and x, so that's x squared. So we're simply going to take the square root of it, and x equals 8.7 times 10 to the negative 14 molar. Call that a day. What's the molar solubility of SrF2? Solid. I didn't write aqueous in this little space, but please know that those are aqueous when they dissociate into their respective ions. Plus 2F minus, and the Ksp here is equal to 7.9 times 10 to the minus 10. Now please remember this is x and this is 2x. So that means this is going to be x times 2x squared. So that's going to be 4x squared times x, which is 4x cubed. So 7.9 times 10 to the minus 10 equals 4x cubed. And x is going to equal 5.8 times 10 to the minus 4. molar. And that's done. An aqueous solution of SrNO3 is added slowly to a 1 liter of well-stirred solution containing 0.02 moles of F- and 0.1 moles of SO4 2-. At 25 degrees, you may assume that the added SrNO3 solution does not materially affect the total volume of the system. Which salt precipitates first? So in my beaker, I've got Sr2 plus, NO3 minus, and I've got F minus, and SO4 2 minus. So we know that nothing's happening with the NO3. There are no exceptions, all soluble. So what do I have? I have Sr, SO4, and I've got SrF2. This is solid. This is going to be Sr2 plus SO4 2 minus, and this is going to be Sr2 plus 2F minus. So let's do one at a time. Here we've got X. SO4 they told us was 0.1, and this is 1 to 1. So I've got Ksp, which if I look up in A24 is 7.6 times 10 to the minus 7 equal to X times 0.1. So X is going to equal 7.6 times 10 to the minus 6 molar. Over here, I've got X, and I know my F minus 0.02, so my Ksp is going to be equal to, for SrF2, 7.9 times 10 to the minus 10, which is equal to X times 0.02, and that's going to be squared. And when I solve for X, I get 1.98 times 10 to the negative 6. So SrF2 is the first precipitate to form because it happens when the concentration reaches 1.98 times 10 to the minus 6 in the solution. So the concentration is lower. It takes less concentration for it to form. And the last one, it says, what is the concentration of the strontium ion in the solution when the first precipitate forms? We just figured that out. It was 1.98 times 10 to the minus 6 molar. That's kind of weird the way they wrote that. In this last question, you're missing the ending. I wrote it in red. As more strontium nitrate is added to the mixture, in C, a second precipitate begins to form. At that stage, what percent of the anion of the first precipitate that remains, what is the percent of the anion of the first precipitate that remains in solution? So, just so I know what we had SrF2, and the precipitate first formed when the concentration was 1.98 times 10 to the minus 6 molar, and the SrSO4 would be precipitates second, and that won't happen until it gets to 7.6 times 10 to the minus 6 molar. So, using the first expression, or the Ksp of the SrF2, you have 7.9 times 10 to the minus 10. That was the Ksp of SrF2 equals, now you're going to put this in, 7.6 times 10 to the minus 6 molar times x squared. So when you solve for x, you get the concentration of F minus equal to 0.010. But they want to know what percent of the anion of the first precipitate that remains in solution. So you started with 0.02. 0.010 is basically F minus now. F minus initial was 0.020 times 100, so that's going to be 50%. Has reacted away already. Okay, that's it for chapter 15. Next we're going to move on to entropy and more about enthalpy.